samarium vacancies.
Yeah. Okay, so thanks a lot for inviting me to the next workshop. And yes, we will talk about samarium hexaborate and a very classical technique compared to what was shown right now. And so just immediately I want to give credit to my grad student, Mike Valentine, who did the experimental work. And for samarium hexaborate, so we took many samples from different labs. Immediately, I have to tell, since we look at some very sample dependence, and basically one of the results of our work that you have to be careful with samples, I have immediately to know the disclaimer that every lab produces kind of good samples or variety of samples, so it's not like some lab has better somehow worse samples. It's just also about control of this particular properties of the samples with different techniques. So we had samples from Fisk, and we had samples from Charles Macklin lab in Johns Hopkins, and we had samples from Jeffrey Young. And so, since I'm the first in this few talks about samarium hexaborate, which was already mentioned here, though, just to remind that this compound was around for many, many years, and I don't count the number of publications about this, but one of the nice papers which I was reading about it dates from 1977, and it's definitely not the first, right? So the compound was around for many, many years, and it's a mixed valence compound, which means that if you go with a fast probe, then kind of X-ray, we see samarium 2 plus and samarium 3 plus, and the slow probes see that an average valence. And for me, who is like a newcomer to this field, it's still amazing that in the situation the material doesn't border, but instead it creates hybridization gaps. So F and the orbitals of samarium hybridize, and then it becomes a Conda insulator or Conda semiconductor. I think that terminology just varies, but talks about the same thing. And this hybridization gap, which was studied before, it was somehow shown by the group of Pierce-Coleman that it could be a basis for the gap of the band inversion, which would then make samarium hexaborate a candidate for a Conda topological insulator. Right? And so that was, I think, the moment where people started to come back to this material and look at the properties and look for the topological insulator properties. So here, as far as I see from the literature, that this metallic, so the topological insulator, Conda insulator shows up in resistivity as it increase. This is on a low temperature part of it, but the resistivity starts to increase at around 150 K, and it goes through the metal insulator transition. But then, since even before this work appeared, it was shown that there is a metallic plateau at very low temperatures. And now people did various experiments which indeed confirm yes, this metallic plateau comes from the surface state, and this in particular is a figure from Jeffrey Proglionis' work. And so they polish the crystal down and they look at resistivity and see, okay, this plateau just kind of stays when the crystal is small, and basically the insulating part increases. So then, what is the nature of this metallic state? It is still a discussion if it's a topologically protected state or it's polarized surface state. This is something we're going to still discuss. There are a lot of other things which are not all consistent when people are looking at samarium hexaborate, and there was a thing which was like a sensation. It's a work from Richard Sebastian's group, where they see 3D quantum oscillation in samarium hexaborate, where they kind of still think that this is metallic. And so all this kind of inconsistency also made me interested in it, especially. So, well, how can we look at the biomagnetized topological insulator, and our inspiration to start to work with samarium hexaborate was this phase diagram from Bruscona's group, which tells that this is a strong topological insulator at when the samarium balance is between 2.56 and 3. And so ideally you want to drive the system into trivial state and look how the gap closes, right? And so the ideal way to do it would be to apply pressure, because it's known for samarium hexaborate, again from a long time ago, that if you apply pressure, you increase samarium balance. We didn't have at this point this possibility, so what we thought of doing is to look at different doping, basically at samarium hexaborate with different number of vacancies, because it's known again that if you create a samarium vacancy, then you drive the average balance of the system to kind of high values, right? And samarium hexaborate, so there's this cubic crystal where we have the boron cage, and what chemists tell me that the boron cage is very robust, but samarium can actually be relatively easy. One can create samarium vacancies. And so what we were looking at, we looked at very few crystals with samarium vacancies and or without them, and what we did, we wanted to follow the bulk gap. Yeah. And so again, I have to say that we were completely not the first people who were looking at the bulk gap, and there are a lot of measurements, and I list here only optical measurements, which there was all measurements from the group of Martin Dressel, which show that there is a gap of 90 millieV. Raman scattering, which I'll be showing, also was done in these materials in the end of 90s by the group of Lance Cooper, and kind of some of the low frequency and very pure crystal results is actually with this frequency and range of samples we reproduce their results. And now, a little bit later today, there will be a talk from Nicolorita from Peter Armitage group, who actually also did their heads, and they actually see that compound is much more metallic than what was reported in optics before. And okay, so what we did, we decided to take a few crystals with different samarium vacancies, and so crystals of samarium hexaborate can be grown with two techniques. It's floating zone technique or it's aluminum flux. And with floating zone technique, the crystals were done within IQM by Tyrell McQueen, and they actually published a paper on that. So when what they claim there is that if you grow it with floating zone technique, then samarium starts to evaporate, and so they have this rod, and they start with stoichiometric samarium hexaborate, and then by the end of the road, they start to have vacancies. And though their paper kind of basically describes this process, and they have some claims that maybe some of the results in samarium hexaborate community come out because of the presence of these vacancies, I would say that I don't fully agree with that, but yes, there is this possibility to create samarium vacancies in controllable way in floating zone, but also it's kind of known that people know how to grow crystals with floating zone technique without creating samarium vacancies, and there are, for example, nature scattering is done on floating zone samples, which from what we now know is reliable without vacancies. Yeah, so what we had these crystals from Tyrell McQueen, which they characterize by resistivity, and they basically, this is their rod, and they start with more resistant sample with a little bit of clutter here, and then they have cut, this is cut number 1 cut, and we call it floating zone pure. Then we have a floating zone deficient, which is cut number 4, which is much more metallic already at kind of in resistivity measurement, and it has up to 1% of samarium vacancies, which is a very small number, right? So actually, 1% of samarium vacancies people can distinguish also by looking at X-ray, kind of the size of the unit cell, which differs from pure in like third number after the decimal number. So then kind of so basically this was our calibration for the way, as I will tell, we found out how many samarium vacancies are in our samples using Raman scattering, and then by basing on that and basing some kind of the widths of the phonons which will define disorder, we also chose our purest sample, which was actually an aluminum flux sample. Though aluminum flux sample again they vary in quality, so we kind of took the best we had. Okay, and so we did Raman scattering, and Rudy Hako will talk how you can use Raman scattering for studying strongly correlated electron systems later today. So, but this method simultaneously allows us in one measurement to probe electronic structure by looking at electronic response, right? But looking at interband transition, and it is known that Raman scattering is sensitive to correlation-induced transition, and there is nice calculation from Jim Briggs from some time ago about that. But it also Raman scattering is very sensitive to disorder. So it basically gave us access to the immediately looking at the number of vacancies in the crystal which we have. Okay, and so here are our three crystals which I compare, and so these are boron, Raman actin boron phonons, and the boron cage is very robust, and so we don't see any difference in boron phonons between these crystals, and at room temperature we don't see any difference in electronic background, but there is something different from these crystals happening at very low frequencies. And so the very low frequencies is the range where we see samarium phonons. Then samarium is sitting in the center of symmetry in the unit cell, so in principle it shouldn't be Raman active. And if we start to see some Raman activity, it immediately tells us that there is some low broken symmetry there. So we see two features. One is at 10 MeV and another at 20 MeV. And basically looking at the neutron scattering data help us to interpret these features. And so we see that also the deficient, the 1% deficient sample has the highest intensity of this 10 MeV feature, and then it just decreases. Basically is very, very low in our aluminum flux sample. So what happens at 10 MeV? At 10 MeV, in the neutron scattering, we will see the samarium acoustic phonons, which have very flat dispersion. And so our interpretation, that's this acoustic phonon, which we start to see in the spectra due to the local symmetry breaking, because we have samarium vacancies. And so the other feature, I will not talk about it anymore. So this is a two-phonon scattering, which is apparently mixture of the two-phonon scattering, which we could calculate, and it has a right temperature dependence. Plus, there is an interesting thing which also would be interesting to study in Raman if we can identify it eventually, that there is some mode at 20 MeV, which is a mixture of lattice vibrations and Laus fluctuations. So when samarium 2 and samarium 3 are very different in size, and so when there are Laus fluctuations, with Laus fluctuation, the electrons are jumping between the sides, the lattice has to readjust. And in Raman, in neutron scattering, we actually see very flat voltage to that. So this is a mixture, some overlap, not a mixture, some overlap of two-phonon scattering and this Laus fluctuation. But this mode is most interesting for that. So this mode is acoustic phonon of samarium, right? And it tells us that in the deficient sample, the local symmetry is broken, so we start to see it, and the purest sample just have this phonon and have very little bit. So this is our way to characterize a sample, and this is our way to put them kind of on the scale. So this is our purest sample, and then we increase the number of vacancies. What is important also that Raman is probably one of the most sensitive methods to look at the Samarian vacancies, because if you see kind of the 1% of Samarian vacancies, you can also see with looking at the unit cell, but this kind of in below 1%, which is called this floating zone pure, this is very difficult to identify. Okay, so basically that's ours. Kind of, that's how we ordered the samples, and then we will look at their electronic properties. Yeah. So what can we learn just with Raman scattering? So with Raman scattering, we come with laser polarization, and then we measure response, and we can arrange this polarization differently in the unit cell and against each other, and this is actually a paper from Jack Berry. So we would expect that for a correlated transition, so the calculations are done for D4G, then we have a cubic crystal we measure in the plane, so we basically project the symmetries of this cubic system on D4H. So we will see that in V2G response, we actually expect to see just nothing. Then in A1G and B1G responses, which these are orientations again in the unit cell, then we will probe different parts of the Brillouin zone, and then we will see the change of the shift of the spectral weight to high frequencies. We will see the opening of the gap to electronic transitions. And this is a temperature dependence of the spectra of a mixture of A1G and EG, which is projected on V2G. So then what we see, let's say it's parallel polarization, what we see is that indeed as we lower the temperature, our background, which was basically just linear in frequency, starts to have two features. At first, we have, so that here the spectral weight goes down at low frequencies, and at high frequencies, we at first at the temperature is about 150 K, start to see the feature at 100 millieV, and then at lower frequencies, we start to see this feature at 40 millieV. And so this is the background extracted, so we end up at 15 K, we see two structures, which basically, kind of at this point, we can think about them as two interband transitions within the band structure, low temperature band structure. So just kind of also what is relevant to what the expectation from the Raman scattering, that we indeed don't see anything in the T2G polarization, which was projected on V2G in D4H symmetry. So kind of it, in some sense, confirms, if you think about transitions due to electronic correlation, then that's what expected, that we will not see any Raman response there. And the rest, we see that the features have more or less the same frequency, which we can think about as the fact that the dispersion is very small. We kind of, so, okay. And then, so another thing which we can do, we actually can compare our electronic spectra with the calculation of band structure calculations, which were done for the case for Samarium hexafluoride below the in the contact insulating state. And so this is, there are few calculations done. This is the one which I like, which is kind of, well, agrees with what we see. And they see that actually there is that's multiple bands. And so they see around the X point of the Brillouin zone, they have this band, there are two F bands, and they hybridize with D band, and they basically end up with two bands below the Fermi level and one band above the Fermi level. And I would say that, and that's what kind of the transitions which we see are the two transitions from the lower and from the upper band across the level. And even the energies which are predicted somehow are in reasonable agreement with what we see. So basically, the hybridization gap, which everybody is talking about, is actually kind of lies below this transition, and I think there is some ambiguity on how people are defining the gap, right? Of course, one can talk about the maximum, and that's what is actually done in Lex Cooper work, or how we can talk about where the 40 MeV number comes out. I think that we also can define it as sometimes done in optics of semiconductors as linear extrapolation to zero intensity, and then we will end up at about 24 MeV. Okay, so now we will look actually at what happens with hybridization gap when we vary the number of samarium vacancies. So the spectrum which I was showing will belong to the intermediate case of the pure sample, which we see where we see both features developing. So if we go to the purest sample, then we actually see this. So let's start with high frequencies. So in high frequencies, everything is the same for these three samples. Then if we go to lower frequencies, then for the pure sample, the feature at 40 MeV and the depression at lower frequencies develop much more, better seen than at this intermediate case of photons and pure sample. And then we go to photons on diffusion sample, which we have 1% of vacancies, and basically we see that the high frequency features develop the same, but at low frequency, at low temperatures, the gap never really opens. So we don't see this 40 MeV transition, and we see a lot of intensities at low frequencies. So, so basically, the presence already of 1% samarium vacancies prevents the low frequency gap from opening. And here I have to mention the work from Peter Risberg, which was done some time ago, and that's in some sense very much in line with what Hugh is calculating when he looked at some defects in Peter Bernborn 12, right, and samarium hexaborate. And so he looks exactly at what we do. We look at presence of defects on samarium sites, and shows that there will be as you build the system this way, then you will get the spectral weight in the gap and range to close the gap. So we start actually, he starts to see some effects. Theory starts to see some effects at about 10% of doping, but we actually start to see it at much lower doping. Right? It's interesting kind of to mention here that what we did also, we had a crystal with 20% of terbium doping, and interestingly enough, that the effects in Raman scattering of samarium vacancy or of terbium doping are actually similar. So we start to have enormous large acoustic phenomena, which is why then due to different masses of these atoms, which is basically the intensity tells us how much local defects we have in the lattice. And here we of course close the gap, the low frequency gap completely, but then that much of doping starts to affect also the higher frequency electronic structures. So even the high frequency feature, this transition is shifted down kind of in the direction of closing of the gap. Okay, so now kind of we figured out that at 1% of samarium doping we close the gap, but then what happens if we have a very pure crystal or we have a crystal with less than 1% of samarium vacancies? So here we can look at very low frequencies, and this is a pure sample where we have very nicely developed 40 MeV feature and hybridization gap, and in the gap we find this very sharp feature of the exciton transition, which actually here, this exciton transition was discussed a lot, and it was seen in neutron scattering and in the work of Wes Cooper on Raman scattering, and was discussed a lot. And there are various ways to now are shown both polarizations, so it has a different orientation. We look at the black spectrum, it has different orientation and different polarization, so basically it shows that there is some dispersion in the feature. How to explain this thing? There are various theories, and the first very one of the first ones were, since we see multiple features, then it was the paper was talking about crystal field levels modulated by phonons, but the simpler ways to talk about this feature is this spin exciton, which is again, there is a work of Peter Risberg, who apparently did everything in this compounds before it became a topological candidate for topological quadrant insulator, where the exciton is formed due to antiferromagnetic interactions, or there is a recent work which is where we even takes a simplified model where the exciton is appearing in the gap due to electron-electron interactions. So, whatever the nature of this exciton is, it actually could be for us a measure of how many states, electronic states, we have in the hybridization gap. And so, if you look now at low frequencies of our three samples with samarium vacancies, then we see that, this is 1% and 1%, we don't have even the gap opening, so we don't expect exciton to be there. And then if we have a pure sample, then we see a sharp feature of exciton with the half-bits of half a millielectron volt. But then if we add some number of vacancies, which is below 1%, then we end up with a widened feature. So, but it's 3 times wider. So basically, or intuitively, you think, okay, the lifetime of the feature just decreased because we have some state to which it can decay inside the gap. And there is a nice description of it was kind of done a bit long ago for the next crystal field levels, which would be interacting with degenerate electrons, and the width. Basically, there is a nice theory which shows how the width is proportional to the square root of the density of states of the electrons here. So we basically can, with the width of this exciton, we can identify that even at numbers which are below 1%, samarium vacancies which are below 1%, we already see some considerable density of states in the gap. And this is kind of then its important point, it's kind of the starting point to look at people's data, because a lot of times it's characterized as resistivity, and this is probably also a very reliable method, and our results do coincide with resistivity, and basically the samples which have an exciton like that, they do have a metallic plateau, but it's not so distinct, and the samples with very sharp exciton have a very distinct metallic plateau. So, however, if you look at various papers, like papers of 3D oscillation, then they say, okay, we are sure that we looked at some vacancies, and we're sure we have below 1%. However, we see that below 1% can still give you a considerable number of states in the gap. Okay, so I actually will conclude, and basically, I think that Raman scattering is one of the optimal ways to look at the quality of samarium hexaboride crystals, and we see this nice features which basically provide the low frequency, low temperature electronic structure, and and we basically show that whatever is happening in samarium hexaboride, you can expect the conduit topological insulator behavior only for very, very pure crystals. Less than 1% of samarium vacancies will start to put states inside the gap. And I think that the variety of results in the field of samarium hexaborate basically also, in some sense, I don't want to go any place, but might depend on the fact that it's very difficult to identify very small amounts of samarium vacancies. However, they can bring some bulk metallic response. Okay, so thank you for your attention.
Questions? Hirsch.
What is the symmetry of that excitonic dissipation?
So it is experimentally, right?
Experiment.
So it is seen in at different, so basically it is this EG, so it's seen at different frequencies at different symmetries. So in 2G,
One second, I missed
yeah, okay.
It's a resonance, it cannot be, so then you have more than one resonance. Right?
Yeah, so well, I actually thought that it basically shows that it has a dispersion. Because with different symmetries, we probe different parts.
No, you're probing everywhere you're probing Q0, you can't probe the gates. You can't probe dispersion easily, but you can say what is the symmetry of that excitation. And by that, you can probably say which of the theoretical moments are relevant. But did I understand correctly that it appears in at more than one frequency?
Right. So it depends. No, so there are two things, let's say. So there is a sharp feature which appears at different symmetries at different polarization. At different frequencies at different symmetries. Right? So then let's say, okay, hopefully we can probe the dispersion. In addition, there are also smaller features, and that was actually a reason for Lance Cooper interpreted as some interaction of phonons with crystal field excitations. The interesting thing is that basically in the theoretical model of Luder, they look and they see that kind of, if they look at the interaction of this crystal field with phonons, that they have several features and some of them have basically purely electronic response, another purely phonon response. And so purely electronic is basically this kind of shocking.
On pure experimental graphs, you can do experiment with different polarization as
Right.
we discussed. We have 6 proper polarizations.
Right.
From which you can say in what symmetry, what is the
Right.
usable representation
So
of the sharpness.
this is EG, which is then if you think about the P1G, this is P2G. So this is actually all the symmetry thing is done in Lance Cooper work. I'm kind of not showing that in the screen.
Keith, I have maybe a sort of similar question about what you call a acoustic phonon mode. You showed a dispersion curve there, but I couldn't quite pick it off. And it seemed like the value of about 10 MeV is not near zero wave vector, but up.
Right.
How do you do that? How do you have optical access to such a high wave vector?
So because of disorder, right?
Yeah.
So basically disorder immediately breaks all the K dependence, and then we integrate with the whole grid.
Absolutely. So,
Yeah.
so do you view that as basically like a longitudinal acoustic mode, and you're seeing something essentially averaged over a bunch of high wave vectors where it's not very dispersion? It doesn't have much dispersion.
Yeah. So you can think about it in two ways, right? Either you can think about it as that we stop to have, because of disorder, we stop to be sensitive to the K dependence, and we integrate with the whole rhythm zone, and because of the flat dispersion, then we kind of have a sharp peak, right? You can also think about it as because of disorder, we start to see all local vibrations, and then kind of the frequencies.
Yes, and this is why, why I wasn't sure about calling it longitude or calling it acoustic phonon. Right? Of course, in the latter case, I wouldn't think of it. For example, I wouldn't think of that as a propagating one.
Right. So this is something which, probably the correct way to look at it is just, okay, it's local vibrations of samarium within the places where there is samarium vacancy, right? On the other hand, people do have this, I would say, trick, basically telling that environment, okay, you lose K dependence and then you have the
No,
integration.
sure, it will resemble a hybrid vector.
Yeah,
It's an empirical.
No, sure.
It's an empirical.
Okay, yes.
Can you comment on the Hansen results of the British group? They have involved 37 Spider-Man Aurora. Do you know about the samples?
right. So I'll be very honest. At first I was very skeptical after I did this work. And I was very skeptical. I thought, what they write in the paper that they have less than 1% samarium vacancies. If I look at my data, I see if I have less than 1% of samarium vacancies, I still have some density, non-negligible density of states within the gap, and that might be the reason for 3D escalations. So when I talked to Suchitra Sebastian, I started to be much more confident in what they're doing, because she does say that they have variable amplitude of oscillations, and they basically, the more defects they have in the crystal, the less of the amplitude. And she claims that they see these 3D oscillations only in the purest samples.
So
So
what samples they have?
They-
Flux or floating zone?
right now, she said that they have everything, that they tried everything. I have to say that, so I think that
The
it's,
one that's published?
sorry?
The one that is published?
The published, I think, is floating zone, but I have to defend floating zone samples, because floating zone samples, which we had, were grown in such a way that there could be some evaporation of samarium. The people who do it, make the samples floating zone, they know how to prevent this. And as an example, there is a work from Hans Braham group where they did neutron scattering on the floating zone samples, which is very, very large, and they see this exciton, which is very, very sharp. So, and we actually also measure Raman spectrum of that sample, and we see this exciton, and we don't see the defects. So this is a kind of floating zone samples grown in cautious way.
Any more questions?
So a quick question about this exciton. Do you know about the excitation dependence? Have you tried other excitations?
No. And I think, so I'm trying to actually, I was not busy with this exciton so much, because actually that's the thing which is done very exclusively in our Cooper work. As far as I remember, we did green. They did green and also red for a different measurement of independent magnetic field, and I think they see it in the same place. So it's worth to look up that papers, but I think they don't have much dependence on this excitation.
Okay, let's thank our speaker again.
Thank you.